Now that you have studied techniques of integration, techniques like integration by parts, integration by partial fractions, when you encounter a problem, it's important to know when to use these techniques and when the problem is in the so-called basic form, and you just simply need to apply one of the standard integration formulas. And the best way to learn the difference between these problems is by experience. So let's start on some examples. Let's start with the integral dx over x squared minus 4. Okay, now having studied integration by partial fractions, hopefully you recognize this as, or it's 1 over x squared minus 4, which is 1 over x plus 2 times x minus 2. And this can be rewritten as a over x plus 2 plus b over x minus 2. Remember, in partial fractions, the idea is to, it's an algebraic technique, really. It's not a calculus technique. It's to rewrite the problem so that it breaks into simpler problems, each of which you know how to integrate. Now, before you even start this, you should quickly look to see, is it in basic form? It's not, because you don't have a du over u. In other words, if you had an x upstairs or 2x, you could work out a du over u deal. But here, it's not. And we're going to do this by partial fractions. Now, we look at this. And what we do is we multiply both sides by the denominator on the left. Okay? So when we multiply here by x plus 2x minus 2, it goes out. You're left with 1 equal to, now when you multiply the right side by x plus 2x minus 2, each term gets its own x plus 2x minus 2. So a over x plus 2 times x plus 2x minus 2. The x plus 2's cancel. You have a times x minus 2. And b over x minus 2 times x plus 2x minus 2. The x minus 2's cancel. B times x plus 2. And what we have to do is determine the constants a and b. Okay, there are two methods to do this. We have 1 equal to a times x minus 2 plus b times x plus 2. There are two methods for doing this. One method is the method of substitution. You go through this expression and you pick values for x, which look convenient, to solve for a and b. You need to pick two values for x, two different values, so you'll wind up with two pieces of information to determine a and b. In a problem like this, when you have linear, non-repeated factors, okay, substitution method is a good choice. For example, we can let x equal 2. If we let x equal 2, we get that 1 is equal to a times 0. 2 minus 2 drops out, plus b times 2 plus 2. Or 1 is equal to 4b, from which we see that b is equal to 1/4. Okay, picking another convenient value for x. Of course, we're going to pick x equals minus 2, because that's going to make this term disappear. So we let x equal minus 2, and we get 1 equal to, now a times minus 2 is minus 4, plus b times minus 2 and plus 2 is 0. So we have minus 4a equals 1, so a equals minus 1/4. So we have determined the constants a and b. The other method is known as equating coefficients. In this, we multiply out the right-hand side here. We have 1 is equal to ax minus 2a plus bx plus 2b. And we try to group like terms together. We have here ax and bx. So we're going to make it a plus b times x, and then a minus 2a plus 2b. And on the left side, we have 1. Now, you could think of this as really 0x plus 1. Okay? Now, in equating coefficients, we look and we say in order for this to be identically equal to 1, it has to be that the coefficient of x has to be 0, and the coefficient and the constant here has to be 1. In other words, this has to match up to be 1, so this has to be 0x plus 1. Okay, so we know that a plus b has to equal 0, and minus 2a plus 2b has to be equal to 1. Okay, if we leave the minus 2a plus 2b equal to 1 alone, and we multiply the top equation through by 2, giving us 2a plus 2b equals 0, and we add the equations, the minus 2a and the plus 2a cancel each other out. We get that 4b equals 1, b equals 1/4, which is what we found out before. And in addition, we have, for example, a plus b equals 0, so a equals minus b, a is equal to minus 1/4. The same information that we had before. A is minus 1/4, b is equal to 1/4. Now, generally, when you're learning partial fractions for the first time, you really love the substitution method. It seems much easier than equating coefficients, but that is only when you have these linear, non-repeated factors. Once the linear factors are repeated, or you have quadratic factors, then it turns out the equating coefficient method is generally better. And we're going to see another example later on. But it's your choice, and as long as you get the right answers, we don't care which way you do it. So we have found out that a is minus 1/4 and b is equal to 1/4. So what we've done is basically changed our problem around. Instead of integrating 1 over x squared minus 4, this is now equivalent to integrating, what's 1 over x squared minus 4? It's minus 1/4 over x plus 2 plus 1/4 over x minus 2 dx. Okay, so instead of integrating 1 over x squared minus 4 dx, we have now seen that 1 over x squared minus 4 is algebraically equivalent to minus 1/4 over x plus 2 plus 1/4 over x minus 2. So this problem can now be, instead of integrating this, we're going to integrate these two smaller problems, simpler problems to handle. Okay, I'm going to finish this up over here. I'm going to erase this and continue the problem underneath. Now, the simplest thing to do here is to break it up. And remember, constants can always be pulled out in front of the integral sign. So it's going to be the integral of this plus the integral of that. And these constants I'm going to pull out in front. So I'm going to make it minus 1/4, the integral of dx, or 1 dx over x plus 2, plus 1/4, the integral of 1 dx over x minus 2. And now the original problem, which we couldn't handle, has now been broken into two problems that are simply du over u. If u is x plus 2, du is 1 dx. This is a du over u. This is the same thing, du over u. So minus 1/4. Now the integral of du over u is natural log of the absolute value of the denominator, and then plus 1/4 natural log of the absolute value of the denominator plus c. So this technique of partial fractions is really just this algebraic method of rewriting the original problem so that it breaks into simpler problems that you know how to integrate. Okay, so we've just done the integral of dx over x squared minus 4. Now suppose the problem had been x dx over x squared minus 4. Now, I'm not going to say that you can't do this by partial fractions. You could. You could do the same procedure, x over x plus 2 times x minus 2, and break it up to a over x plus 2 and b over x minus 2, just like we did before and solve for a and b, but that's silly. Before you approach the problem by any of the techniques of integration, partial fractions, integration by parts, trig substitution, whatever, you should first check to see, is the problem in basic form? Is it one of your standard integrals that you're supposed to know? And this, of course, is. Okay? If u is x squared minus 4, du dx is 2x, du is 2x dx. And this is almost in the form du over u. If you were to multiply by 2 on the inside here and divide by 2 on the outside, this would become 1/2 the integral of du over u, 1/2 natural log the absolute value of u plus c, 1/2 natural log of the absolute value of x squared minus 4 plus c. Could you have done this by partial fractions? Yes, but it would be silly for you to take the time to do it. Always check to see if the integral is in basic form. Is it one of your standard integrals that you learned earlier in calculus? Okay, and this one is. Okay, now let's look at the example x cubed over x squared minus 4 dx. Okay, it starts off looking similar to the ones that we've just done, except it's certainly not du over u. And we notice, what's more, that the numerator does not have degree less than the denominator. The general rule when integrating a rational function, a quotient of polynomials, is if the numerator does not have degree strictly less than the denominator, you should start by long division. You should divide. Okay, and here we have this situation. The numerator does not have degree less than the denominator. Now, x cubed divided by x squared minus 4 means x squared minus 4 goes into x cubed. Okay? X cubed divided by x squared minus 4, exactly what it says. Now, how many times does x squared go into x cubed? It goes x times, and then we multiply x times x squared is x cubed. X times the minus 4 is minus 4x, and we subtract. X cubed minus x cubed, 0. 0 minus a minus 4x comes out to be 4x. And we can rewrite our original problem, x cubed over x squared minus 4, as the quotient x plus the remainder 4x over the divisor x squared minus 4. The same way, if I had, for example, 7/3, this means 7 divided by 3. How many times does 3 go into 7? Twice. 2 times 3 is 6. Subtract 1. We can rewrite this as the quotient 2 plus the remainder over the divisor, 2 and 1/3. This is, of course, equivalent to this. 2 is really 6/3, and 1/3 is 7/3. If you understand this, you should be able to follow this. It's the same thing. In 7/3, writing it as 2 plus 1/3. The same idea. You do the long division. It's the quotient plus the remainder over the divisor. Okay? So let's go back and finish this problem. We had x cubed over x squared minus 4 dx. But we now know that x cubed over x squared minus 4 can be rewritten as x plus 4x over x squared minus 4, which breaks into two simpler problems. The integral of x dx plus, I'm going to take the constant out, 4 times the integral of x dx over x squared minus 4. Okay, now the integral of x to the first power is, of course, x squared over 2. We just did this problem. We needed, if you remember, if u was x squared minus 4, du was 2x dx. We multiply by 2 on the inside, divide by 2 on the outside. This becomes 2 times the integral of exactly du over u, or 2 times the natural log of the absolute value of x squared minus 4 plus c. Remember, this integral is now du over u. So it's 2 times the integral of du over u, 2 times ln of the absolute value of u plus c, or 2 times ln of the absolute value of x squared minus 4 plus c. For our next pair of examples, let's try integrating x squared e to the x cubed. dx, and x cubed e to the x squared dx. Okay. Now, the first of these is the one in basic form. This one is really an e to the u almost du problem. If you rewrite this as e to the x cubed times x squared dx, if u is equal to x cubed, du would be 3x squared dx. If you were to multiply by 3 on the inside, divide by 3 on the outside, this would become 1/3 the integral of e to the u du, which is 1/3. Of course, the integral of e to the u du is simply e to the u plus a constant, giving us a final answer of 1/3 e to the x cubed plus c. And of course, you can check this by differentiating and showing that you do, in fact, get x squared e to the x cubed. Well, that's the easy one. Now we come to this. X cubed e to the x squared dx. It's not in basic form, because if I have u equal to x squared, du is 2x dx, and this is not what I'm left over with. Okay, what am I going to do? The natural thing to try when you have a mixture of algebraic and transcendental, a product of algebraic and transcendental functions that's not in basic form, is integration by parts. In the last problem, worked out very nicely. I said let dv be the most complicated thing that you know how to integrate that's in basic form. If you try to let dv be e to the x squared dx, you can't integrate that. u is x squared, du is 2x dx. Okay, what you shouldn't do in this case would be let dv be x cubed dx, or it's to say, okay, this is the most complicated thing I know how to integrate. Okay, what's going to happen if you do integration by parts by letting dv be x cubed dx is that the next integral is going to be worse than the first one, not better. Okay, don't jump to the assumption that the most complicated thing you know how to integrate is x cubed dx. It's not actually true. Okay, if you can possibly make the transcendental part of the dv, that's the way to go. What we're going to do here is to change the x cubed into x squared times x, and now call this u and this dv. And instead of treating it as x cubed, treat it as x squared times x. Take the x, mix it with the e to the x squared, and call this dv. So if u is x squared and dv is x e to the x squared dx, let's see what happens. Then du is 2x dx, and v. Okay, I'm going to try to integrate both sides now. This is almost in the form e to the u du. If you were to rewrite this, putting a 2 in here and a 1/2 in front, this is 1/2 the integral of e to a power times the derivative of the power. So it's just 1/2 e to the x squared plus c, which we're going to hold off to the end. So we were able to figure out what v is. V is 1/2 e to the x squared. Okay, so let's see what we can do. This is going to be uv minus the integral of v du. uv, x squared times 1/2 e to the x squared minus the integral of v, which is 1/2 e to the x squared du, which is 2x dx. So what do we have? We have x squared over 2 e to the x squared. I'm going to take out the 1/2 minus 1/2 e to the x squared 2x dx. I could have taken out the 2 also, but I happen to notice that this is in the form e to the u du exactly, so I didn't want to take out the other 2. Okay, I took out the 1/2, and I see e to the power times the derivative of the power. So this is easy enough to finish. It's x squared over 2 e to the x squared minus 1/2. Now the integral of e to the x squared 2x dx, or e to the u du, is e to the x squared plus c. Okay, now I want you to look at 3 problems that look alike, but actually 2 of them are fairly straightforward and basic form, and 1 of them requires integration by parts. Okay, we have 3 problems up there, all involving ln x. Now, the question is which are in basic form and which require integration by parts. We know that these involve a mixture of algebraic and transcendental. Here also, it turns out that the first and the last are really in basic form. Let's see if we can understand that. If we let u equal ln x, then du dx is 1 over x, and du is 1 over x dx, or dx over x. So it turns out that this problem, which is ln x times 1 over x dx, or dx over x, is exactly the integral of u to the 1 du. And to integrate u to the 1 du, you get u squared over 2 plus a constant, or ln of x squared over 2 plus a constant. So this was in basic form. Now, the second of these is not in basic form. I guess precisely for the same reason that the first one was. In other words, if u is ln x, du is 1 over x dx. So that substitution isn't going to work here. If u is ln x, you do not have du. This is not a u to the 1 du. Okay. So here we're going to try integration by parts. Here the most complicated thing that I can integrate is simply the dx. I'm going to let that be dv, and this be u. Okay? Have no real choice here. The only choices are for dv or dx, or the whole thing, ln x dx, which of course you can't integrate. What is not a choice is letting dv be x dx. You cannot separate the x from the ln. Okay? That's not an option. So, letting dv be dx and u be ln x. So u is ln x, dv is dx. Let's see. I've been writing them underneath, so let me do it this way. Du, of course, is then 1 over x dx, differentiating and integrating both sides. V is equal to x. So this is now going to be rewritten as uv minus the integral of v du. uv is x ln x minus the integral of v, which is x. Du is 1 over x dx. uv x ln x minus the integral of v du. X times 1 over x dx. So this becomes x ln x minus the integral, the x's cancel, of 1 dx. Or x ln x minus, now the integral of 1 dx is just x plus c. X ln x minus x plus c. Now in this problem, you see a fraction. You might be trying for du over u. A common mistake would be to let u be the whole denominator here. This is a product. It would be the first times derivative of the second, which would be 1 over x, plus the second times the derivative of the first, which would be 1. So du dx is 1 plus ln x. So clearly, du, which would be 1 plus ln x dx, is not what you have upstairs. Okay, so if u were to be equal to x ln x, the whole denominator, du, in order to integrate this as du over u, would be 1 plus ln x, and you're off by much more than a constant, so that's out. We didn't do anything wrong. We just made the wrong guess as to what u should be. Integration is an inverse operation, and any time when you're doing an inverse operation, a certain amount of guesswork. When you first learned how to do long division, you would try it. You were in 3rd grade, you say, does it go 6 times? And you tried it, and you said, oh, it's too big. And you tried 5 times. You didn't do anything wrong. You were guessing. We're guessing here as to what substitution to make. This doesn't work. However, if you were to rewrite this as, say, dx over x over ln x, in other words, and let u simply be ln x, then you would have du over u. In other words, nobody says that u has to be the entire denominator. Anything that you don't want in the denominator, any factors that you don't want, can be moved into the denominator of the numerator. For example, if I have a over bc, I can rewrite this as a over b divided by c. Because when you're dividing by c, you're really dividing by c over 1. You can invert and multiply by 1 over c. And that's what I did here. Instead of a over bc, I made it a over b, and I left c alone in the denominator. Now, it's exactly du over u. In other words, if you were to let u be ln x, the way we did before in all the other examples, then du would be, du dx would be 1 over x, and du would be dx over x, 1 over x times dx. And this problem would be exactly the integral of du over u. So this would be ln of the absolute value of u plus c, or ln of the absolute value of, now what is u? Ln x plus c. The nice thing about the substitution is it enables you to write something that you might at first glance think is incorrect. As you're going by the book, you see it's du over u, ln of the absolute value of u plus c, and if somebody gives you a question in x, you give them back an answer in x, okay, for an integration problem. And then you have no choice but to let u be ln x. So you're writing ln of the absolute value of ln x plus c, but since you're going step by step, you know you've done the right thing. For my next pair of problems, let's try the integral of 9x cubed plus 4x over 6x squared, and the reciprocal, the integral of 6x squared over 9x cubed plus 4x. Okay, now, dealing with a rational function. Quotient to polynomials. The numerator does not have degree less than the denominator. So, first step is long division. But since the denominator only has one term, we can actually just break it up, which is the same thing as division. In other words, if you have a plus b over c, that's the same as a over c plus b over c. We usually, when you're learning arithmetic, working with fractions, we go this way. As if you're adding 2 fractions, they have the same denominator, 2 7s and 3 7s. You combine the numerators, 2 plus 3, and get 5 7s. That's the way you're used to doing it, but there's no reason that you can't work it the other way. If you have 2 or more terms over the same denominator, you can break it up, put each term in the numerator over the common denominator. You can break up tops, but not bottoms. Okay, only numerators can be broken up in this way. So what I'm going to do is to break this problem up. Instead of a plus b over c, I'm going to make it a over c plus b over c. A plus b over c, I break it up into a over c plus b over c. But to understand, that's the same thing as long division. Now, let's see if we can simplify a little. What do we have? Dividing the top and the bottom here by 3, we can make this 3 over 2. And dividing top and bottom by x squared, we are left with x. So 3x over 2, or 3 halves x for that, plus here, dividing top and bottom by 2, we're left with 2 over 3. Dividing top and bottom by x, you're left with a 1 on the top and an x on the bottom. So 3x over 2 and 2 over 3x. Now this can be broken up into 2 simpler problems. Let's take the constants out. Well, the integral of this plus the integral of that, but I'm taking the constant out. So instead of the integral of 3/2 x, I'll make it 3/2 the integral of x dx. Instead of 2 over 3x, I'll make it 2 over 3, now the integral of 1 over x dx. And each of these, of course, can be handled easily. This is 3/2. The integral of x to the 1 dx is, of course, x squared over 2 plus 2/3. The integral of dx over x is ln of the absolute value of x plus c. So 3/4 x squared plus 2/3 ln of the absolute value of x plus c. Now, at first glance, we're looking at a rational function. The numerator has degree less than the denominator, so we don't have to use long division. Your first instinct might be to say, oh, I can factor the denominator into x times 9x squared plus 4. And you might be thinking in terms of partial fractions, because after all, we have a linear factor and an irreducible quadratic. That's usually the way we go on something like this. However, you should always look to see if the problem can be simplified. And of course, this problem can be simplified. We can cancel an x top and bottom. In other words, this is 6x squared, which is x times 6x, over 9x cubed plus 4x, which is x times 9x squared plus 4. And if you cancel the x's, divide top and bottom by x, this problem reduces to something that does not need partial fractions. This is just the integral. You can take the 6 out if you want. 6 times the integral of x dx over 9x squared plus 4. And this is almost in the form du over u. If u is 9x squared plus 4, du would be 18x dx. So if you were to multiply by 18 on the top here and divide by 18 in front, this becomes 1/3 the integral of du over u, or 1/3 natural log of the absolute value of u plus c, or 1/3 the natural log of the absolute value of 9x squared plus 4 plus c. Of course, you do not need the absolute value here because 9x squared plus 4 couldn't be negative anyhow. In fact, it's always positive. Okay, so we looked at this problem and its reciprocal. The original problem required division. The second one didn't, and we were ready to start partial fractions when we realized that we could reduce the problem. It turned out to be just du over u. Now, what if the problem, instead of having 6x squared, okay, the problem we just did was 6x squared over 9x cubed plus 4x. Okay, and here we could reduce this by dividing top and bottom by x squared, by x. Here, suppose it was 6x squared plus x plus 2. Okay, then we have a rational function, quotient of two polynomials. The numerator does have degree less than the denominator. And here there's no easy way out. Here we're going to need the partial fractions. So let's see what we can do. Let's do the work over here. And we'll come back and fill it in later. So we have 6x squared plus x plus 2 over 9x cubed plus 4x, which we've already seen can be factored to x times 9x squared plus 4. And to set this up with partial fractions, we have a linear non-repeated factor. And for that, I'm going to have a constant over the linear factor. We have a quadratic, an irreducible quadratic factor. And in the numerator of that, I'm going to put a typical linear expression, bx plus c. Once I've done that, I'm going to multiply both sides by the denominator on the left. If I multiply the left side by x times 9x squared plus 4, they cancel. I'm left with just the numerator on the left. If I multiply this term by x times 9x squared plus 4, the x's cancel. I have a times 9x squared plus 4. And if I multiply this by x times 9x squared plus 4, the 9x squared plus 4's cancel, and I have bx plus c times x. Now, this can be done by substitution. The only easy value that you can substitute in for would be x equal to 0, and that would at least make certain things drop out. But after that, since you don't have the linear factors, you could try whatever numbers you want. You might try x equals 1, x equals minus 1. In general, instead of trying 1, 2, and 3 or something like that, I find that it's usually more successful if you try, if you're trying 0, say 1 and minus 1, 2 and minus 2, as many as you need. In this case, of course, you only need 3. So you might try 0, 1, and minus 1. However, in this problem, I think the equating coefficients method is really the way to go. If I write this 6x squared plus x plus 2, what do we have? I have 9ax squared plus 4a plus bx squared plus cx. And I want to make the right side look like the left side. The left side is something times x squared plus something times x plus a constant. So I have two terms with x squared. So I'm going to make it 9a plus bx squared. Then for x, I only have one term, cx, and then the constant 4a. Now I want to match this to 6x squared plus 1x plus 2. The only way that's going to happen is if 9a plus b becomes 6, c is 1, and 4a is 2. Then this would be 6x squared plus 1x plus 2. So in this particular problem, the equating coefficients actually works better than the substitution, because we have now 9a plus b equals 6. But we immediately have that c equals 1 and that 4a equals 2. So this tells me that a is equal to 2/4 or 1/2. We know that c is 1. And 9a plus b is 6. So 9a, but I know a is 1/2. So 9 times 1/2 plus b is 6. So b is 6 minus 9/2. 12/2 minus 9/2, or 3/2. 9a plus b is 6. 9 times 1/2 plus b is 6. b is 6 minus 9/2, 12/2 minus 9/2, or 3/2. So now I know what a is. A is 1/2. b is 3/2. And c is 1. So I'm going to go back and I'm going to finish up this problem by integrating, instead of the original problem, a over x and bx plus c over 9x squared plus 4. So let's see what we have. We can write this as a over x, so that's 1/2 over x plus bx plus c, which is 3/2 x plus 1 over 9x squared plus 4. I'm going to make this 1/2 the integral of dx over x plus, now here I'm going to make it 3/2 x over the 9x squared plus 4 and 1 over the 9x squared plus 4. So 3/2 x, I'll take out the 3/2, be x dx over the 9x squared plus 4, and then 1 dx over 9x squared plus 4. So this is going to break into 3 problems, each of which I know how to handle, because they're all in basic form. Okay, I made it 1/2 over x, 3/2 x over 9x squared plus 4, and then 1 over 9x squared plus 4 to be integrated. And I took out the 1/2 and the 3/2, the constants in front. Okay. What do we get? Now, this, of course, is just du over u. So this first one is going to be 1/2 natural log of x plus a constant which we'll save to the end. This is almost a du over u. If u is 9x squared plus 4, then du would be 18x dx. If I multiply by 18 here and divide by 18 in front, I would have 3 over 36, or 1 over 12, the integral of du over u. So 3 goes into 18, 6 times 1/12, the integral of du over u. 1/12, integral of du over u, or 1/12 ln of the absolute value of u plus c, or ln of the absolute value of 9x squared plus 4, plus the last one, which is dx over 9x squared plus 4. Now that's almost in the form du over u squared plus a squared. If you rewrite this as 3x quantity squared plus 2 squared, 9x squared plus 4, I made this is almost du over u squared plus a squared. Okay, if u is equal to 3x, du is 3 dx. du dx is 3, du is 3 dx. In this problem, of course, a is 2. So if you put a 3 in and a 1/3 in front, this becomes, we have this, we have this. You don't really need the absolute value there. Plus 1/3 the integral of du over u squared plus a squared. But you should know that that, of course, is 1 over a inverse tan u over a plus c. So let's finish this up. 1/2 ln of the absolute value of x plus 1/12 ln of 9x squared plus 4 plus 1/3 times, now, 1 over a inverse tan u over a plus c, or 1 over 2 inverse tan u over a is 3x over 2 plus c. So 1/2 ln the absolute value of x plus 1/12 ln of 9x squared plus 4 plus 1/6 inverse tan of 3x over 2 plus c.